Welcome to this coding walkthrough. In this session, we'll explore problem number 1109 titled Corporate Flight Bookings. We'll break down the problem, analyze different approaches, and guide you through an optimal solution. Let's dive in. In this problem, we are dealing with a corporate flight booking system where we need to manage seat reservations across multiple flights. The input includes an integer, n, which represents the total number of flights, numbered sequentially from 1 to n. Along with this, we are provided with a 2D array called bookings. Each entry in this array specifies a range of flights and the number of seats booked for each flight within that range. Specifically, each booking is represented as first, last, seats, where first and last define the inclusive range of flights, and seats gives the number of seats booked for each flight in that range. Our task is to calculate the total number of seats booked for each flight and return the results in an array called answer, where the value at index I corresponds to the total seats booked for flight I plus 1. The input constraints further explain the size and structure of the input. The number of flights, n, ranges from 1 up to 20,000, meaning we can have a very large number of flights to process. The bookings array can also be substantial, with up to 20,000 entries. Each entry in the bookings array is structured as first, last, seats, where first and last specify a valid range of flights from 1 to n. The number of seats booked in each range, represented by seats, can be as high as 10,000. The output of our solution should be an array of size n, where each element represents the total number of seats booked for the corresponding flight. Now, let's look at some examples to understand how this works practically. In the first example, we have n equals 5, meaning there are 5 flights, and the bookings array contains 3 entries. The first booking specifies that 10 seats are booked on flights 1 and 2, so the total seats array starts as 10, 10, 0, 0, 0. The second booking adds 20 seats to flights 2 and 3, updating the totals to 10, 30, 20, 0, 0. Finally, the third booking adds 25 seats to flights 2 through 5, resulting in a final total of 10, 55, 45, 25, 25. This array is the output, as it shows the total seats booked for each flight. Let's consider another example to reinforce this idea. In the second example, we have n equals 3 flights and 2 bookings. The first booking specifies that 5 seats are booked on all flights from 1 to 3, so the total seats array begins as 5, 5, 5. The second booking adds 10 seats specifically to flight 2, updating the totals to 5, 15, 5, which is our output. In the third example, with n equals 2, there are 2 flights and 2 bookings. The first booking reserves 100 seats on flight 1, leading to 100, 0, and the second booking reserves 200 seats on flight 2, resulting in 100, 200. This final array is returned as the output. These examples highlight how the booking ranges and seat counts are applied incrementally to produce the results. To solve this problem efficiently, we must account for some important constraints and edge cases. First, the number of flights, n, and the number of bookings can both reach 20,000, so any naive or brute force approach that processes each booking individually for all flights would be too slow. Additionally, bookings are always valid, meaning the flight ranges given will fall within the total number of flights. We must also consider edge cases like having only one flight, where all bookings apply to the same flight, or having only one booking, which simplifies the task to processing a single range. When the input size is large, with n and the length of bookings both at their maximum values, the solution must be efficient enough to handle the data in linear time, ensuring scalability and performance. The goal is to design a strategy that efficiently applies the bookings to the flights and computes the results without unnecessary computations. To solve this problem, we start by considering the brute force approach. The intuition here is straightforward. For every booking request, we directly update the number of seats for all flights in the specified range. For example, given a booking that spans from flight start to end with a value of x, we increment the seats for each flight in this range by x. The algorithm involves initializing an array to hold the seat counts, then iterating through the range for each booking and applying the updates. While this method is simple and easy to understand, it has a significant drawback. Each booking potentially requires iterating through a large range, and with multiple bookings, this leads to a worst-case time complexity of n squared. This makes it impractical for larger inputs, where the number of flights and bookings can grow significantly. The brute force approach, while intuitive, is not scalable and becomes computationally expensive as input size increases. This inefficiency prompts us to explore a more optimized method. The inefficiency in the brute force approach lies in repeatedly updating overlapping ranges. To address this, we use an optimized technique called the difference array. Instead of directly updating all elements within a range for each booking, we optimize the process by only making two operations, incrementing the start of the range and decrementing the position right after the end of the range. The difference array works by storing these incremental changes, and the final seat counts are derived by taking the cumulative sum of this array. This approach drastically reduces the number of updates required per booking to just 2, regardless of the range size. For the implementation, we initialize a difference array with one extra element to handle boundary conditions. For each booking, we add the booking value at the start 1 index of the difference array and subtract the value at the end index. Once all bookings are processed, we compute the cumulative sum of the difference array to obtain the final result. This method is not only more efficient but also reduces the time complexity to O(n) plus bookings, as processing each booking is O(1), and calculating the cumulative sum is O(n). While this approach introduces the added complexity of understanding the difference array, the trade-off is a significant improvement in performance, especially for large inputs. Given the constraints of the problem, the optimized approach using the difference array is the clear choice. While the brute force method offers simplicity, it is not scalable for large datasets. The optimized solution, with its O(n) plus bookings, time complexity, efficiently handles scenarios where the number of flights and bookings can reach up to 10,000. The key insight here is that the cumulative sum of the difference array allows us to transform the incremental changes into the final seat counts, eliminating the need for repetitive range updates. This makes the algorithm both fast and memory efficient. By leveraging the difference array, we significantly reduce unnecessary computations, enabling the solution to scale well with larger inputs. In conclusion, the optimized approach strikes the right balance between performance and clarity, making it the ideal strategy for solving this problem effectively within the given constraints. To understand this problem, imagine there's a series of flights, and each booking request specifies a range of flights that need seat reservations. For example, a booking might say to reserve seats for flights 2 through 4. Our goal is to determine the total number of seats booked for each flight after all requests are processed. One straightforward way to solve this is the brute force approach. This method involves processing each booking request individually. For a request covering a specific flight range, we iterate through those flights and increment their seat counts by the specified number of seats. While this method is easy to implement, it becomes computationally expensive when there are many bookings or when the flight ranges are large. Let's explore why this approach is inefficient and how we can improve upon it. Now, let's break down the brute force approach step by step. First, we start with input parsing. We receive two main inputs, the total number of flights and a list of booking requests. Each booking request is given in the format start, end, seats, where start and end define the range of flights, and seats specifies the number of seats to be booked. Next, we initialize an array called seats with a size equal to the number of flights, all set to 0. This array will track the cumulative seat bookings for each flight. For example, if there are 5 flights, our array starts as 0, 0, 0, 0, 0. After initializing, we process each booking request. For every request, we convert the 1-based indices start and end into 0-based indices to match the array. Then, we iterate through the range of flights specified in the request and increment the corresponding elements in the seats array by the specified number of seats. After processing all requests, the array will contain the total seats booked for each flight, which we return as the final result. To see how this works in practice, let's walk through an example. Suppose we have 5 flights and 3 booking requests, 1, 2, 10, 2, 4, 20, and 3, 5, 25. First, we initialize the seats array as 0, 0, 0, 0, 0. Then, we process each booking one by one. For the first booking, 1, 2, 10, we increment the values at indices 0 and 1 by 10, resulting in the array 10, 10, 0, 0, 0. Next, we handle 2, 4, 20, incrementing indices 1 through 3 by 20. This updates the array to 10, 30, 20, 20, 0. Finally, 4, 3, 5, 25, we increment indices 2 through 4 by 25, leaving us with the final state, 10, 30, 45, 45, 25. This array reflects the total seats booked for each flight. After processing all the bookings, the resulting array is 10, 30, 45, 45, 25. This means that the first flight has 10 seats booked, the second has 30, the third and fourth have 45 each, and the fifth has 25. While this approach works, it has significant efficiency limitations. The need to iterate through the range of flights for every booking leads to a time complexity of O, m*k, where m is the number of bookings and k is the average range size. For large inputs, this can become a performance bottleneck. We also need to handle edge cases, such as when there are no bookings, which should result in an array of zeros, or when bookings overlap, which requires careful accumulation of seat counts. Additionally, for scenarios like having only one flight, all bookings will contribute to the same flight. To address the inefficiency, we can use a more optimized approach leveraging the difference array technique, which significantly reduces the time complexity. We'll explore this optimization in the next section. This solution uses a difference array technique to efficiently handle the range updates for seat bookings. The key idea is that instead of directly updating the seat count for each flight in the range, we record the net change at the start and end plus 1 indices. This reduces the time complexity significantly. ### line-by-line explanation. 1. We define the corp flight bookings function, which takes the booking requests, bookings, and the number of flights, n. 2. We initialize an array seats of size n plus 1 with zeros. The extra element is used to handle range boundaries during the prefix sum calculation. 3. For each booking, start, end, seats_booked, we add seats_booked at the start 1 index to indicate the increase in seats at the start of the range. Subtract seats_booked at the end index to indicate the decrease in seats after the end of the range. 4. We iterate over the seats array starting from index 1 to compute the prefix sum. This converts the difference array into the actual number of seats booked for each flight. 5. Finally, we return the result excluding the extra last element, which was used only to manage boundary conditions. This approach is highly efficient with a time complexity of O, n plus m, where n is the number of flights and m is the number of bookings. It avoids the inefficiency of directly updating each flight within a range for every booking, making it well-suited for large inputs. This is the Java implementation of LeetCode problem number 1109, corporate flight bookings. The logic mirrors the provided Python implementation, where we use a difference array to track seat adjustments and compute the final seat bookings using a prefix sum. Key Java-specific differences include the use of type declarations for arrays and variables, as well as the use of arrays.copyof to truncate the array to the desired length. We begin with a simple example where we are given 3 bookings and 5 flights in total. The first step is to initialize an array called seats with a size of n plus 1 to handle boundary cases efficiently. This array is initialized with all zeros. Next, we process the first booking, 1, 2, 10. Here, we add 10 at the starting index minus 1, which is index 0. This reflects the addition of 10 seats starting from flight 1. Then, we subtract 10 at the ending index, which is index 2, to indicate that the addition stops after flight 2. The seats array now reflects the changes from this booking with values 10, 0, minus 10, 0, 0, 0. Now, let's process the second booking, 2, 3, 20. For this booking, we add 20 at index 1, which corresponds to the start of flight 2. This increases the cumulative seats starting from flight 2. Then, we subtract 20 at index 3, marking the end of the bookings effect after flight 3. The seats array updates to 10, 20, minus 10, minus 20, 0, 0. Moving to the third booking, 2, 5, 25, we add 25 at index 1, further increasing the seats starting from flight 2. We then subtract 25 at index 5 to indicate that the effect of this booking ends after flight 5. The updated seats array is now 10, 45, minus 10, minus 20, 0, minus 25. With all bookings processed, we move on to compute the prefix sum to determine the total seats booked for each flight. To calculate the prefix sum, we start with the first flight and propagate the cumulative sum across the array. For the first operation, we add seats 0 to seats 1, updating the array to 10, 55, minus 10, minus 20, 0, minus 25. Next, we add seats 1 to seats 2, resulting in 10, 55, 45, minus 20, 0, minus 25. Continuing, we add seats 2 to seats 3, updating the array to 10, 55, 45, 25, 0, minus 25. Lastly, we add seats 3 to seats 4, giving us 10, 55, 45, 25, 25, minus 25. Since the last element was only for boundary handling, we exclude it and return the result for the flights as 10, 55, 45, 25, 25. In this edge case, we have a single booking affecting only the first flight, with 3 flights in total. We start by initializing the seats array with size n plus 1, resulting in 0, 0, 0, 0. Processing the booking 1, 1, 100, we add 100 at index 0 to reflect the seats added starting from flight 1. The array updates to 100, 0, 0, 0. Then, we subtract 100 at index 1 to indicate the end of the booking after flight 1. The updated seats array is 100 minus 100, 0, 0. To compute the prefix sum, we start by adding seats 0 to seats 1, resulting in 100, 0, 0, 0. Then, we add seats 1 to seats 2, leaving the array unchanged as 100, 0, 0, 0. Finally, we exclude the extra boundary element and return the result as 100, 0, 0. This correctly reflects that only the first flight is booked with 100 seats, while the other flights remain unaffected. Now let's examine a case where all flights are booked equally. In this example, we have a single booking that spans all 3 flights, with the booking 1, 3, 50. We initialize the seats array with size n plus 1, resulting in 0, 0, 0, 0. Processing the booking, we add 50 at index 0 to indicate the start of the booking from flight 1. The array updates to 50, 0, 0, 0. Then, we subtract 50 at index 3, marking the end of the booking after flight 3. The updated array is 50, 0, 0, minus 50. Next, we calculate the prefix sum to get the total seats for each flight. To compute the prefix sum, we add seats 0 to seats 1, updating the array to 50, 50, 0, minus 50. Then, we add seats 1 to seats 2, resulting in 50, 50, 50, minus 50. Excluding the extra boundary element, we return the result as 50, 50, 50. This shows that all 3 flights have been booked with 50 seats each, validating the correctness of our approach. In analyzing the time complexity of our solution, we can break it down into 2 main steps. First, we process the bookings. The algorithm iterates over the bookings list, which contains m bookings. For each booking, we perform 2 constant time operations, updating 2 specific indices in the seats array. This means the total time for processing all bookings is proportional to the number of bookings, or OM. Next, we calculate the prefix sum. Here, we iterate through the seats array, which has a size of n plus 1, starting from index 1 up to n. For each index, we perform a single addition operation to compute the cumulative sum. This step takes n time. When we combine these 2 steps, the overall time complexity becomes m plus n, which simplifies to n plus m. The time complexity of this solution remains n plus m, regardless of the scenario, whether it's the worst case, best case, or average case. This is because the algorithm consistently processes all m bookings and calculates the prefix sum for the entire seats array of size n. Shifting to space complexity, the primary contributor is the seats array, which is initialized with a size of n plus 1. This requires n plus 1 space, which simplifies to n. The bookings list is part of the input, so it doesn't add to the space complexity. Additionally, the algorithm uses a few auxiliary variables for iteration and computation, but these require only constant space. Therefore, the overall space complexity is determined by the seats array, resulting in n. When comparing this optimized approach to a naive solution, the difference in efficiency becomes clear. A naive approach would iterate through each booking and directly update all flights within the range, start to end. With m bookings and n flights, this would result in a time complexity of m*n. The space complexity, however, would remain O(n), as we still need to store the results. In contrast, our optimized solution uses a difference array combined with a prefix sum. This reduces the time complexity to O(n plus m), a significant improvement over the naive O(m*(n), while maintaining the same O(n) space complexity. To confirm this mathematically, during the processing step, each booking contributes O(1) updates to the seats array, leading to O(m). In the prefix sum step, each of the n flights is visited once, contributing O(n). Since these steps are independent, their time complexities add up to O(n plus m). Additionally, the largest storage requirement, the seats array, determines the space complexity as O(n). This demonstrates the efficiency of our optimized solution within the problem's constraints. One of the most common mistakes when solving this problem is using a brute force approach, where for each booking, you iterate through all flights in the range from start to end. While this method seems straightforward, it has a time complexity of O(n*(m), which becomes highly inefficient for large inputs and can lead to time limit exceeded errors. Another frequent issue arises from misinterpreting the range indexing. Many problems specify flight numbers using 1-based indexing, but arrays in most programming languages like Python or Java use 0-based indexing. If you don't adjust for this difference, you may encounter off-by-one errors. Additionally, it's easy to overlook edge cases, such as when start equals end, which represents a single flight booking, or when the number of flights is minimal, like n equals 1. Finally, when using the optimized difference array technique, it's crucial to update values at the start index and the end plus 1 index. Forgetting the adjustment at end plus 1 can lead to cumulative errors in your solution and incorrect results. Another source of bugs can occur when constructing the prefix sum from the difference array. If you fail to initialize the result array properly or accidentally iterate out of bounds, the computed seat allocations will be incorrect. Now, when you're in an interview setting, efficiency is often a key focus. Interviewers expect you to transition from a brute force approach to an optimized solution like the difference array technique, which achieves a time complexity of O(m plus n). It's important to articulate why this optimized approach is better. Additionally, communicating edge cases demonstrates your thoroughness. For example, you might mention scenarios like single flight bookings, no bookings at all, or handling maximum input sizes. Recognizing patterns is also valuable. This problem is part of the broader category of range update problems, which often involve cumulative sums or segment trees. Finally, be prepared to explain trade-offs. For instance, you should discuss why the brute force approach is not scalable and how the difference array reduces complexity and performs better for large inputs. There are several related problems that utilize similar techniques or concepts. For example, LeetCode 238, product of array except self, involves prefix product calculations, which are conceptually similar to prefix sums. Another related problem is LeetCode 1094, carpooling, which is a range update problem that also leverages the difference array technique to handle updates efficiently. LeetCode 370, range addition, is another direct application of the difference array concept, making it a great practice problem. And of course, the problem we're currently discussing, LeetCode 1109, corporate flight bookings, falls into the same category. Solving these related problems can help reinforce your understanding of range updates and the difference array approach, as well as prepare you for variations that might appear in technical interviews. When considering alternative approaches, the brute force method is often the first solution that comes to mind. This involves iterating through the range of flights for each booking and incrementing the seat count for each flight individually. While simple, this approach is inefficient with a time complexity of O(n*(m). A more optimized solution is to use the difference array technique, which handles range updates efficiently. By incrementing the start index and decrementing the n plus 1 index, you can mark the range and then compute the prefix sum to get the final seat allocations. This reduces the complexity to O(m plus n). For more advanced scenarios, such as when dynamic updates are required, a segment tree can be used. However, this is typically overkill for problems with static input. The key trade-offs to consider include simplicity versus scalability. The brute force approach is intuitive but doesn't scale well with large inputs, whereas the difference array is slightly more complex but highly efficient. On the other hand, while segment trees offer flexibility for dynamic updates, their complexity makes them unnecessary for static problems like this one. Great job completing this session. To recap, we solved corporate flight bookings using an optimal difference array approach, achieving excellent time efficiency. Remember to practice similar problems to strengthen your understanding. Thanks for watching, see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!